Okay, good afternoon, everyone. Let's get started. We came to the end of almost to the end of our syllabus policies. The last one is about diverse student support. I don't have time to go over all of them, but the point of this policy is to say that there are lots of affinity groups here at the University of Utah, and it might be worthwhile to just check which one are here, and maybe you would like to join some of them. So just so you know that also a bunch of these resources exist over here. Okay, while we are at the end of syllabus, let's also go over some of our deadlines. So as I'm sure you are aware, today is the deadline for our third homework. Next Wednesday, we requested the data collection report from you. So try to meet your teammates soon and try to write that report soon, and try to make it very concrete in terms of what data you have, which is the goal of data collection report. We want to see that you are on a very, very good to have all the data you need. You don't need to collect all the data, but it must be clear that you have set everything in motion for collecting the data you have. So in case you are scraping some data and the collection still lasts, that's okay. But it's clear that things are on a good track to be, done rather soon. Today we have released the fourth homework, which is on clustering. Basically, after the lecture today, you will know everything you need to solve this one, so you can start working on it right away. And it is due, as always, 2 weeks from today. Okay, I guess that's all about the announcements. Any questions from you about homeworks, projects? Okay, that's good. All right, let's get started then. Last time we had covered one type of clustering algorithm, hierarchical or agglomerative clustering, and we have finished on the note of how to validate those clusters, and we kind of turned that question into saying, is the number of clusters we have chosen good? And then I told you I will go over a few more ways to validate clusters. I decided to first cover today k-means, and then which is another clustering algorithm, and then we'll go back to that question of cluster validation at the end of today's lecture. To talk about k-means today, and k-means is usually referred to as two things. Sometimes we are referring to specific k-means algorithm that we will go over in detail today. But also it is good to think about it as a problem formulation. A lot of clustering algorithms can be thought of as k-means algorithms, but they are not exactly the most popular one. So just so you know, that sometimes this will refer to a family of clustering algorithms rather than the specific one we are going to talk about today. And with k-means, we are going to take our n examples like the last time, and we are going to cluster them into k-hard clusters, which means that unlike with hierarchical clustering, we will not allow that certain examples are put into clusters. So we are placing our n examples into k-hard clusters. And the idea behind the k-means problem formulation is that you are going to, let me try to illustrate it with an example. So let's say we have a two-dimensional input space. Let's say that we on the y-axis have salary, and on x-axis we have age. And let's make up some points here. Okay, So with k-means formulation, you are going to start with k, which is the number, capital K is the number of clusters you have, or you're trying to achieve. And let's say we have here k equals 3. We just decided using some way of deciding that we are going to cluster these data points into 3 clusters. With k-means formulation, you are going to start with some random centroids. Remember last time centroids were those representatives of the cluster when we work in a Euclidean space. So we start with a few random, not few, but exactly 3, because that's the number of clusters we have chosen. And then we are going to, in the next step, group our data points to the cluster corresponding to the centroid which is closest to that point. So, for example, these points here, they are closest to this first centroid. Then we have this second cluster here and the third one here. All right, now that we have done that, we are going to adjust our centroid. We are going to move it to the center of its cluster, right? So this one is going to go somewhere along here, and this one will go here, and this one will go here. Now, we need to, again, check whether now data points to which centroid they are closest to. So let's see whether any of them had now, are they now closer to any of the other centroids. And it seems like from the way I have drawn this that they're all still in the same cluster. And this is where we would stop with our clustering technique. If now imagine, although this is not the case, this point here is closer to this cluster here, we would make this group of points a new cluster. This would be the other one, and this would stay the same. So we regroup them. And now you would again need to change the centroid of your new clusters. And this one stays the same. So that's the basic idea of k-means clustering formulation. And now what we are going to do is more formally see why are we putting points to the clusters of their closest centroid, and why are we choosing the centroid to represent the cluster. So kind of give more formal motivation for this thing I have just illustrated for you. Okay, so let's write that more formally. I need to find a better solution for this. Okay, so the first thing we are going to introduce is what's called criterion or error or cost function. And that's basically the function you are trying to minimize with your clustering approach. Or cost or error. You might find it under lots of names. And let's use as our criterion function the sum of squares of the Euclidean distances of each example from its centroid. So we are going to have k clusters, capital K clusters. In each clusters, we are going to then iterate over all data points in our input space. We are going to check whether that point is in the current cluster, CK. So remember, this is indicator function. It's 1 if xi is in cluster CK and 0 otherwise. And we are going to multiply it by L2 norm of the difference between the data point and the centroid of the kth cluster. Okay, so this guy here, that's centroid of CK. Okay, so if we are trying to cluster our data points to minimize this function, it's kind of obvious that what we need to do is to try to minimize the distance between the point and the centroid, right? That seems like the thing which will minimize this function. So that's what we are going to do. We are going to define a new variable here, BIK, to be equal, again, indicator function, and it's going to be 1 if k is argmin of the distance between xi and the centroid of cluster Cj. All right, so this is 1. If k is the argmin, it's the cluster where the distance of the point xi to its centroid is the smallest. And that kind of enforcing that will minimize this function j. Okay, so now basically your problem has 2 parameters. It is these BIKs and these centroids. And because they're kind of dependent on each other, this whole minimization of this function j with respect to these parameters b and c, it doesn't have closed form solution. So we are going to write that, no closed form solution. So what we do when we don't have closed form solution, we do this iteratively until we find something that's a good approximation. So we are going to then randomly initialize our centroids Ck for every k, element from 1 to k. And then we are going to assign each point, each xi to the cluster with mean distance between xi and its centroid. Okay, or in other words, we are just going to choose this BIK. It's the same thing. All right, now that we have fixed our BIKs, the only parameter here that's relevant are our centroids. What are the centroids that minimize this function j? And when we are finding the parameter that minimizes a function, we are going to take the gradient of that function and find the value at which this gradient is 0. So if we take the gradient of our function j with respect to C centroids, if we calculate that, so this is what we are calculating the gradient of, we are going to get 2 times sum of 1 to n BIK that are now fixed times xi minus ck hat or bar. And this has to be 0. And now if you solve this equation with respect to ck, you're going to get that ck has to be equal to sum of that goes from 1 to n of BIKs times xi over sum of 1 to n of B1k, which is actually exactly the average of the points in the cluster. So here under the fraction line, we have exactly the size of the cluster CK. And then above fraction line, we have 1 to n of, excuse me, not 1 to n, but all elements that are actually in CK. Okay, so starting from this criterion function j that we wanted to minimize, we have worked out exactly the type of algorithm that I have illustrated with example before. We start with randomly initialized centroids. but we are then assigning points to clusters such that they are part of the cluster where the distance between that point and that centroids is the smallest relative to other centroids. And then we are computing centroids to be exactly the average of the points in the cluster. So it didn't appear out of nowhere. It kind of came from this formulation, depending on this criterion function J. Okay, I hope that's clear how we came to that illustration. I will just write the algorithm in a form that is more easier for you to follow later. So k-means
First is also maximizing the distance between the centroids.
I don't think so. But let me see, can I make my intuition more formal? Yeah, I don't think there is anything that specifically enforces this. And we will look at, so here we started with random initializations. We are going to look at some other initializations that will enforce that things are farther apart from each other. But looking just at this function J, I don't think anything is strictly enforcing that behavior. Yeah. Okay, let's write the whole algorithm. So as I said, k-means can mean two things: problem formulation or the specific algorithm. I now am going to write the k-means algorithm, but you will also find it under the name of Lloyd's algorithm. Okay, so we start with our endpoints, x1 to xn. We have then randomly initialized. All right, excuse me. We need to then choose k. So you must decide on k before you start clustering. Then you're going to randomly initialize your k centroids, ck, for every k from 1 to capital K. And then we are going to do those two steps. We are going to, just a moment. The first step is that for every point, we assign that variable, BIK. That's 1 if K is argmin of all clusters. If we look at the distance between xi and its centroid. Okay, that's how we assign our points to clusters. And then for every centroid, we are going to update it by taking the average of the current cluster CK. Okay, that's a whole thing, right? And convergence here means that basically you don't change centroids anymore, and therefore the points don't change anymore. So there is nothing to be changed, as we have seen in the illustration I gave you. I didn't know which point would now be closer to any other clusters, and there was nothing to do. So let's go over some of these properties. First of all, these variables will be either 0 or 1, which means that this is hard clustering. You do not allow that your point is assigned to two clusters, only to one. Let's look at the efficiency. Before I go into efficiency, I want to stop and just check that so far this is clear. Okay, Just wait a little bit. I see you still right. Okay, so let's look at the efficiency. So calculating this part here, that will be O D. So where D is the dimension of each point. So that's in RD. Okay, then here we will have O of D times N. We have, again, D dimensions, and we have N points, at most N points that can appear in a cluster. And what else do we need here? So here OD is only for calculating the Euclidean distance, but then we need to do this multiple times, right? We need to do it for K clusters and N points and then times D. We are comparing each point to the centroid of each cluster. There are N points, there are capital K clusters, dimension for Euclidean distance, everything gives us K times N times D. And in the end, we also have multiple iterations of this, right? So we repeat this a certain number of times. Let's call capital T to be, let it be the total number, the number of iterations. That means that the whole thing is O of T, D, and K. And this is not a problem in terms of T being way smaller than our number of points N. So we have way less iterations than we have our points. We are going to cluster, so we don't get complexity that's of N square, which we had with hierarchical clustering. And it's linear in all relevant parameters, which is way better than hierarchical clustering. So efficiency relative to hierarchical clustering is much better. All right, let's look at some other properties. Is this whole thing deterministic? It does depend on the choice of the initial centroids we choose, but if we set a random seed to a certain value and then with that value of random seed we repeat this experiment, then we should get the same cluster out of our algorithm. So that's one thing you can check. There is also another less obvious part of the randomness can come from here. So here where we are checking which cluster, which centroid is closest to our point. Two clusters, two centroids could be equally far away from a given point, and then you need to decide where to put that point because it's equally apart from two clusters. And what you would do here is you would just randomly assign it to one of these. But again, if you want this whole thing to be deterministic, this random choice has to be fixed. So you fixed your random seed with Python random, and then when you repeat this thing, it's going to give you the same output. So it is deterministic. Will it converge? It will converge because we have a finite number of possible partitions of N points into K groups. So we will have K to the power of N possible partitions. And the way we are doing this algorithm is to minimize this function J. And in each iteration, we are going to decrease the value of function J. And once we can't decrease it anymore, we will stop. So we are increasing all the way until we can. Is it optimal? Does it find the best clustering that we can find? Unfortunately, it does not. So it is a greedy algorithm, and that means that it will find locally the best solution, but not globally. So, for example, we can illustrate this with this example. So here, let's say we have these points. Let's say we have chosen randomly these two points as our centroids. Then the way we are going to cluster our points is like this. In the next stage, we are going to change centroids to these values, and that's where we stop. So basically, these points will never be reassigned, although the better actual partition for these points is these two clusters. Okay, so just because we were making these greedy choices, we ended up with something which is not the globally the best solution. Okay, so the point here is that your k-means algorithm will highly depend on the choice of the initial centroids that you choose. So natural question is, can we do something better than just randomly picking points? And there are some options for that. Okay, so let's go over choosing initial centroids. So our option 0 was to pick them randomly. All right, the second option is to not choose any point in this space as your centroid, but choose one of the points you are trying to cluster randomly as a centroid. So maybe we can show this. Let's say we have something like this. Okay, so previously we would choose two randomly, for example, this as our centroids, that's our initial option 0. But with our second option, we are going to choose one of these points as our centroids. Okay, so I will write that down. Randomly choose k points from xi as centroids. Yep.
Would we randomly choose one of the centroids on each iteration, or once we choose a centroid, does it remain the same on every iteration?
This is only about the initial choice of centroids. Once you choose them, using one of these options, we are going to go over now, but the rest of the algorithm stays the same. We are always going to take the average of the vectors inside the cluster to be the centroid. So this is only about the initialization of these centroids in the beginning. Yeah. All right, so why would anyone want this? Well, if we are choosing points that we are actually going to cluster, most likely we are not going to choose some random points that are super far away from our clusters, doing all the damage like we have seen in the previous example. So that's kind of the benefit of doing this approach. The problem is that we might have some kind of outlier here. And then if we choose randomly this outlier, then we are going to make a lot of trouble for us, because then we are going to, let me make a new picture just to not confuse you. Okay, so same kind of set, but now we have this outlier. And we have chosen, let's say, this point as one centroid, and we have been very unlucky and we chose this outlier as our centroid. And what will happen then is that we will likely, now I need to make it farther away. Okay. So then what will happen is that this whole thing will become a cluster, and this one outlier will become another cluster. And although it's reasonable to want that outlier to be its own cluster, there is the density of this gigantic cluster we have just made is really sparse, and that's not what we want as well. So this is also not a great solution in case we know that our data might have some outliers. If you are 100% sure your data won't have outliers, then this won't be a problem, and this might be a reasonable thing to choose. Okay. So another thing you could do is, I will move to another page. You could measure or construct centroid of all points you are trying to cluster, and then add k small random vectors. And I think it will become clear what we are trying to do here if I again draw some examples. So even if you had an outlier here, if you take the average of all of these points, you will end up somewhere where you are kind of close to each one of these blobs, including the outlier. And then when you add two small random vectors, you will get something that's not terribly far away from all the points, no matter how spread they are. Okay, does this make sense? No? What is unclear here?
So you're choosing the center of all the points,
Mm-hmm.
and then you're adding vector. Okay.
Yeah, you just choose capital K random vectors, and you add it to the center. So you like move a little bit from the center of all the points. So you are still not super far away from all the points.
And
Yeah.
Completely out. Okay.
Yeah, and in this way you kind of fixed your problem of outliers. All right, and then the option you might have heard about from before, it's called k-means plus plus. And this goes maybe together with this intuition that you ask about choosing centroids that are farthest away from each other. So you would randomly choose one point xi as your centroid. And then for every other centroid you need to choose, so centroid from 2 to capital K. So for every K from 2 to capital K, you are going to choose a point that is farthest away from the previous centroid. Okay, so you're going to choose next, right, let's say choose next CK. Such that, and it's a little bit more nuanced than what I said. I said we are going to choose the one that's farthest away. We're actually going to choose a point that has high probability. Sorry, we are going to choose. We are going to set our whole thing such that those points that are farther away from our previous centroids have higher probability of being selected. And why wouldn't we just choose the one that's farthest away rather than using this probability? I will explain that in a bit. So we are going to choose next CK such that points that are farthest from previous CK. All right, let me just write this a little bit differently. So choose next CK plus 1, such that points that are farthest from previous centroids CK have higher probability of being selected as CK plus 1, the new centroid. Okay, the reason why we are working with probability here should be clear with an example. So again, if we had these blobs and some outlier, then if you had chosen, let's say, this point here as your centroid 1, then if we are just taking the farthest point, we would take this outlier, right? This one. Which brings us into that situation we had before, right? Where now we are going to probably cluster the outlier as being one cluster and everything else as the gigantic other cluster. So with the probability, what is happening is that it's considered that here we have lots of far away points, right? And although this one is the farthest, there is more of these other ones which are still far away, but not as far as that little outlier. So probability of selecting them will actually be higher than selecting the outlier just because there will be more of them. Okay, so with the introducing the probability, you are going to, on average, in expectation, select those that are far away, but not so far away that they are an outlier. Okay, and to define what that, how to define that probability, it can be something like CK probability of choosing the next one as x1, given our data points and previously selected centroids, equals to, we're going to take above fraction line mean of all clusters, their distance to xi over sum of Cj mean k ck minus xj. Okay. This kind of formulation will give you that desired behavior, that those that are farther away will have higher probability of being selected as the next one. Okay, so this is called k-means plus plus. I said that working with this probability is better because then we have we don't have the problem of, we likely don't have a problem with these outliers, but you can also use the version where you do take the point that's just farthest away. So we can write this down, randomly choose 1 point xi as a centroid, and then choose next centroid to be the farthest xi from all previous centroids. And this will be called, known as under the name of Gonzalez. which is the name of the person who has first proposed this. Now, you will see in the materials, for example, in M4D book, that this will also be just called k-means algorithm or Gonzalez algorithm instead of just the means to initialize centroids. And the reason for that is that you could find the centroids like that, and then you can cluster your points and say that's it. You don't do things iteratively. More often, these are known as just initialization techniques for the Lloyd's algorithm we have seen before. So you would use this to either k-means plus plus, the most often k-means plus plus to initialize your centroids, and then you would do the iterative approach we have seen in the Lloyd's algorithm. Any questions about this? Yep.
For calculating the probabilities like regions, how would you like implement that?
Well, you have this formula for probability. You just need to implement the formula. It doesn't have anything else to it. Yeah. So you have k centroids, you have endpoints to check whether the next centroids is one of these points. You would calculate this fraction, and then you would pick xi that has the highest value for this. Yep. Okay, so one thing that I didn't say explicitly, but it might have been already in your mind, is that we kind of introduced this in the Euclidean space, right? With this function j here that we are trying to minimize and model, that has the Euclidean distance embedded in it, and that assumes that we are working with points xi that are represented as vectors of real values. And as we have seen in the many lectures so far, we are not always working with Euclidean spaces. So there is a version of this algorithm, Lloyd's algorithm, known under the name of k-medoids. And again, you can think about k-medoids as the formulation for more algorithms rather than just one specific algorithm. So what was centroid in our Euclidean space here, it will be known under the name of medoid. And that will be a representative example from our input space that we are trying to cluster. And then the algorithm that we have used in the Lloyd's algorithm we have used before changes minimally, and that variation is known under PAM, P-A-M-M, which stands for partitioning around medoids. And it works with any distance function you would like to use. So you are going to initialize your set of medoids M to be, and I will still use notation CK just to kind of make it easier to map to centroids from before. But this represents some examples from our set XI. From our input space X. Okay, so we are going to initialize M to selected points XI. We are going to have K of them. And then we are going to repeat a very similar procedure we had with Lloyd's algorithm. So for every data point that is not our medoid, we are going to calculate to which cluster this point should be placed. And we are going to do that in a very similar way we have done in the Lloyd's algorithm with when we had Euclidean distance. We're going to put it into a cluster that minimizes the distance between xi and this medoid of that cluster. Okay. So here I have a mistake. Okay, let me just check that I didn't have this mistake before. All right, that was correct. Okay, very similar to what we have done before. Now, instead of using the Euclidean distance, we are using arbitrary distance. The big thing that has changed is that we are now taking points that are not medoids, and we need to compute the distance arbitrarily. All right, so then we are going to update our medoids such that we have set them to the whatever minimizes the distance between that with other points. Okay. So we take all the points that are not yet considered to be our medoids, and then we are going to check the distance between each point, xi, and that medoid. Right, and we are going to do this until we converge. Okay, so basically things are kind of the same. We are placing every point to the cluster of the medoid that's closest to that point. And when we are updating our medoids, we are, instead of taking the average, because we can't take the average anymore, we are selecting the point that is closest to all the other points in the cluster. Okay, and so here things got a little bit slower because of this part here, where now we are we need to compare every point that's not a medoid yet with all the points that are in a cluster, and then we can have here n minus k times n minus k comparisons, and this will altogether make this whole thing slower. So we will have complexity of O of t, which is total number of iterations, k and minus k squared. So now we have a quadratic complexity in the number of points. Sorry, I put this to be capital K, it should be small k. Okay, and then so not surprisingly, if you would like to make this efficient, there are some variations of this algorithm. I won't go into that, but just know that, you know, since this is not as fast as Lloyd's algorithm was, then there was like a wave of variations that try to speed this up. So if, for example, if you're trying to use this for your projects and you have huge data set and things get fast, search for faster variants of this algorithm, you will find it very quickly. Okay, so now, as promised, I want to go back to the cluster validation that we have started to talk about last time. Okay, so I will just quickly go to the notes from the previous lecture. So this is what the node we ended up on. And so one thing that maybe wasn't clear when I was describing this last time is that we are talking about cluster validation techniques, but a lot of time that question boils down to, did we choose the correct number of clusters? So in clustering, cluster validation and choosing the right number of Ks are kind of similar questions or very related questions. So last time I have said, okay, the first one is just checking the quality. You just sample and examples from each cluster and manually inspect them. Okay, this is not about choosing the right number of clusters. But then the second one was about choosing the right number of clusters. I said you will have your data points, and before you did any clustering, you are going to use some kind of dimensionality reduction technique to put your points in, no matter which dimensions they originally are, into 2D space. And then by looking at this 2D space, you might notice that, wow, I have like 2 clear blobs, which means that your number of clusters should be 2. So then you go and do your clustering where you have set your number of clusters to be 2. You could then later on kind of visually also see whether the clusters you get correspond to those blobs. For example, if you had 2 clusters, you can read all points that are clustered in one cluster with red and blue otherwise, and then it should be immediately clear whether your 2 blobs are now red and blue, or there is some kind of mixture, and that would probably tell you that something might have gone wrong. Then I talked about elbow method, and here I probably missed 2. All right, so this is, we introduced this SSE score, which is sum of squared errors. And now this looks very similar to that criterion function J we have seen before. If you use Euclidean, this is exactly that function J. And what I was saying there is that we will plot something like this. And this again tells you about whether you have chosen the right number of clusters. So what we were doing here is we are having on y-axis our SSC score, and on x-axis we have our number of clusters. And then the regions we were paying attention to is where we have sudden drop and then leveling. Now, what sudden drop of SSC means? It means that you have reduced the error by a lot just by changing, introducing one additional cluster. So intuitively, this means that you probably have captured some natural cluster, because if you have managed to reduce so much error just by introducing additional cluster, that hints that things are going well. And then when you are leveling off, that means, okay, you are not reducing the error much more by adding new clusters. So those clusters didn't have that, you know, this natural capturing of natural clusters didn't occur there. So if you see, you know, what you can kind of check is that, okay, have you chosen, you can kind of plot this thing and see whether you have chosen the number of clusters that would correspond to this sudden drop and leveling regions. What might happen is that you have leveling and then it drops again. So let's imagine maybe here at cluster number 4, here we have leveling, then we have sudden drop and then leveling again. This is also maybe a good number of clusters. So you might see multiple of these, like sudden drop, then leveling, then sudden drop, then leveling. And all of these are potentially good candidates for the number of clusters. So by examining this kind of a plot, you might capture not only one good potential number for number of clusters, but multiple of them. Okay, so that's about elbow method. Again, yet another method to choose good number of clusters, which will then result in a good overall clustering technique. And then I promised to talk about silhouette analysis, and I will talk about some other things besides that. All right, so we have 1, 2, 3, I will put see previous lecture. Yeah, I want to make just one more point that I forgot to say here. So remember last time when I told you you could overfit, and if you have taken a machine learning course, that probably means something to you. If you didn't, it probably doesn't mean anything. What I wanted to say by that is that you can introduce more and more clusters. You can have as many clusters as you have points, right? But that would mean that each point is in its own cluster, and that's a very bad clustering technique, but it is the one that gives you J of 0. So the solution that perfectly minimizes the function J is terrible. So yeah, this introducing more and more clusters and just seeing for a long time that there is this leveling means that you are just introducing more clusters when they are not needed. So yeah, we are looking for that magical number, which is small, not too small, and not too large. Yeah. Okay, let's go into silhouette analysis. All right, so this technique will, as elbow method, be a visual. We are going to make a plot and then inspect that plot. And to produce such a plot, we will need so-called silhouette coefficients, SI, which are calculated like this. I will write something down and then I will explain what these symbols are. Okay, it's going to be in the interval between -1 and 1. Okay, so AI is going to be equal to the distance of all points in a cluster where xi is to xi. Okay, so let's say we have these points. They're all in the same cluster. And then let's say this is our xi. Then the value AI will be calculated by taking the average distance from other points in the cluster with xi. And the value bi is going to be calculated as, all right, bear with me. Okay, we are going to find the cluster where xi is not in, and we are going to find among those other clusters the one where the distance of its points to xi is minimal. So let me write this down. Okay, so this one is the same. So that's where our xi is, that's the one I call ck. Now imagine some other cluster over here and another one which is very far away. Now the distance of each cluster here to xi, calculated by taking the average distance of its points to xi. If we take the average of these pink lines I have just made, they're going to be on average smaller than if I made lines with this cluster below, which I won't do. Okay, so maybe I can make just one. So what we choose here in the end is the average distance of this pink line, which are distances of the points of the nearest other cluster to xi. Okay, so what intuitively all this means, when si equals to 1, then xi is far away from the examples from the neighbor cluster and very close to example in its own cluster. So that means xi is very close to points in ck, where it belongs, and far away from points in other clusters. And this is good. When SI is -1, other extreme, that's very unwanted. That's probably misclustered example. It's an example which is very far away, from points in CK where it belongs, and close to points in other clusters. So now if you check the SI coefficient for each one of your points, and you notice that some of them have values that are very close to -1, that should give you kind of a hint that that something went wrong, and that these examples are misclassified. If we have SI being close to, I'll write it here, to 0, then that means that XI is on the border of two clusters. On the border between two clusters. Okay. But now I want to show you how this looks like if you are using scikit-learn. All right, so in the homework for clustering, I have added few questions about how to code stuff in scikit-learn. Most of them, if not all of them, are not all of them, but some of them are just bonus points to kind of encourage you to use scikit-learn, but you're not enforced to. With hierarchical clustering, I believe I did ask you to use scikit-learn. I kind of want you to start using these libraries because you will never do this kind of stuff on your own. You're just going to pick whatever is there implemented and then apply to your problem. The only issue is that sometimes, for example, with k-means, you have as potential initializations. You can pick, for example, k-means ++, but then you can't choose other ones we have talked about. So you're sometimes limited with the choices you can make. But otherwise, this library have a lot. Okay, so let's go into this silhouette analysis. Okay, I will try to make this as big as possible. All right, so here on the right, we have 2D representation of these points that have been generated for these examples. And obviously, we have here these two blobs. One is here, and the other one could be here, although you can also think about this as 3 separate blobs, right? Okay, so this is our data. And now we had clustered this data, and indeed these points were put in class 1, and all these other points were put in class 0. All right, now we are going to plot these silhouette coefficients. So remember, silhouette coefficients are these values SI. Okay, that's going to be the values, potential values of SI are going to be on our x-axis. And then what we are going to plot is basically, you can imagine it like, either as a, to make it simple, like you just imagine it as a bar plot. You can think of how many, imagine like horizontal bar plots, how many examples have value up to 0, value 0.2. Imagine it's like that. And then you just fill all this space. All right, so that's one thing you're plotting here. And then the red line that you're plotting here, that's the average silhouette coefficient across all the data points in your input space. And the thing you don't want to be happening, which it doesn't happen here, is that all of these or let me say it the other way around. Or you have to have the end here to be above this average silhouette coefficient line. If you have situation like this one, where this point here is lower than the average silhouette coefficient in the entire data set, that suggests that there has been a problem with clustering with that specific cluster group. So with this one, it suggests that this group of points haven't been clustered properly. Unlike this one, which is really good, obviously, because it's over there far away from everything else, and it has this, I don't know, call it maybe tail, far away from the average, as well as the yellow ones. Let's see what else we have here. Now things are getting better, right? We had introduced one more class, and now we had split these two into two separate clusters, and now all these tails are right on this silhouette coefficient, the average silhouette coefficient. If we would introduce another cluster, so we increase the number of clusters to 6, then we split this cluster here. See here, and that resulted in something that's not good, and the silhouette coefficients for those two clusters are less than the average silhouette coefficient line. So I hope this kind of gives you some kind of impression of how you could use this to see whether the number of clusters you have chosen is a good choice to make. Did you have a question?
Keep in mind that some data points are explored by -1 to 0. What actions may be made for improving the final results?
Yeah, I would say it depends whether you have found like a few of them that are misclassified and you are like, okay, these are outliers and I actually don't care about them. There, you can have few of them and they are misclassified, but they're not outliers. Rather, your data is not represented well, which happens a lot when we don't represent different demographic groups very well, and then you have to take more, careful choices there. But in general, for right now, we will talk a little bit more about how to handle outliers later in the class, and how to kind of think about this difference between a real outlier and you just didn't consider some people. But I think you should focus on right now is if a lot of points are not being classified properly. And I would recommend actually just looking at these silhouette plots like this and checking whether things are left to, or to the right of the average silhouette coefficient, rather than inspecting each one of these points individually, for finding the big groups of misclassified examples.
Those numbers not in the data set. Is it better for considering them as outliers or just simply change the clustering techniques?
Yeah, I mean, it only depends on the example, but if we kind of use this example to answer your question, I would say if you find lots of them that are not appropriately classified, I wouldn't consider them as outliers. So for example, here we have found with this silhouette coefficient analysis that we have split a natural cluster into two clusters for no reason beyond just having a too high number of clusters in the beginning. Yeah.
And could you please share this in?
Yeah, of course. Yeah. So you won't be asked about this in homework, but I think it's good to know that you don't need to start from scratch if you would like to do some of this analysis. So some of this stuff can be super useful for your projects, for example, where I think lots of you got feedback from us. If you plan to use clustering, we like to see more analysis than just showing us two-dimensional plot of the data points you have clustered like this one. We want to see more. So this just showing a plot like this won't be sufficient. So know that there are other things you can do, and they're actually implemented in scikit-learn, so you don't need to write everything from scratch. Okay, so I want to go over a few more things you could do. Okay, so one thing you could choose do is something similar to regularization in machine learning. Basically, you can find your number of clusters such that you run your whole algorithm multiple times with multiple values for the number of clusters. And you can choose the one that minimizes not only the function j, the criterion function, but also such that this lambda k is also minimal. Higher this lambda is, smaller k will be, basically. And now you probably are thinking, I'm looking for number of clusters k, and now you just introduced me another parameter. So we just changed the problem of finding the right number of clusters into finding the right number of right value for the hyperparameter lambda. However, there is something called a k information criterion. And it is something that is used outside of clustering. So it's like a broader technique than just what's needed from clustering. I won't explain what it is, but if you apply it to k-means, then you get the following formulation for this regularization problem, that we are looking for the number of clusters k star that minimize jk plus 2 times dimension of your vectors times k. So now you are not having the hyperparameter lambda anymore. You're just having fixed values, 2 dimension of your vectors for your data points and the number of clusters. So you could do that. You can minimize this instead of just function j to find appropriate number of clusters. Yep.
Can you explain what regularization is again, just conceptually?
Regularization is a way to it's a technique we use to find solutions that are simplest but still are good solutions to our problem. So typically in machine learning, you will see this in the context of polynomials. If you have a simple polynomial like this one, it's going to model your data quite well. But if you're allowed to your polynomial to have any coefficients associated with it, you can also have a solution like this, which goes through all of your points, but it's very complex. So when you give it new data, it most likely won't be a good solution for new data. So what the regularization is, it's not a huge point of this class, so I don't want to go more than that. It's just a way to find simplest good solution to your problem. Okay, and the last thing we could do is, so we are doing clustering because we don't have labeled data, right? But we could label a little portion of our data into clusters that we know should exist. And then we could check the accuracy, something similar to accuracy on that sample of examples we have actually labeled. Okay. So let's say you are working on a very specific problem of categorizing your inputs as dogs or cats. So you know you have 2 clusters and they have a meaning to it, right? Dogs, cats. So what you can do is sample number of examples you deem reasonable for you to actually label, and you can label those examples such as dogs or cats. Now you have a small portion of your whole data that you know you know the true clusters for those examples. Okay, so label some data and produce so-called reference clusters. And then all you need to do is determine whether your technique had clustered those examples the way you have done. The same way we do measure accuracy in any kind of labeled machine learning task. There are different choices of that accuracy-like metric you can use, but the one I think you should know is called rand index. And this is basically accuracy at the level of pairs of examples. So basically you will take, I will explain what these things mean. Okay, so A will be the number of true positives. That is the number of pairs that match. So match in a sense, the label you assign to them and the label assigned, the cluster assigned by your algorithm is the same. And then we'll have B to be the number of true negatives, which is the number of pairs that truly do not match. So you have some pairs of your input example. One will be a cat, one will be a dog, and your algorithm will put those pairs of examples exactly to be in those clusters. And then this will be true negative. Okay, and so that's how you would check. You would report your rand index. Higher the value, the better. However, there is a problem here of not being this index is not adjusted super nicely, in a sense that if you get random assignments of clusters, this random assignment of clusters won't get you random rand index of 0. And to adjust it, to get the random assignments to have rand index of 0 and clusters that are identical to have rand index of 1, you would use something that's called adjusted rand index. And I won't go into what exactly that is. I do want to point you again that these kinds of things are implemented. So again, if you go to sklearn metrics, adjusted rand score, you will get the implementation of this. And you don't need to implement it, you just use it for your own clusters and your own reference clusters. Okay, so this is what I want to stop with the validations of clusters. You won't be asked any of these validations like silhouette or elbow method or rand index in your homework, but really think about using them for your projects if you are using clusterings, because that tells us way more than just showing those plots where we can't really computationally quantify how two clustering algorithms differ, where if you introduce these metrics like these ones, we can tell something more meaningful in terms of relative differences between two algorithms. All right, that's all. Thank you.